This is a lesson on resistors and circuits in a unit on circuits. We've covered a lot of basic principles about circuits up until this point. You can look back at my lessons on the basics of circuit analysis where I go over the different components of circuits. And the basics of current goes over what you need to know about currents, thinking about current flow. And we're also dragging along with us V equals IR from the lesson on Ohm's law. In the prior lesson, I had given this sort of strategy for circuit analysis with Kirchhoff's rules. So this is something that we are going to use consistently. Again, these come from the basic principles of the cosmos, conservation of charge, which is the junction rule, and conservation of energy, which is the voltage rule. So you can use these with all circuits. So what I want to look at, and keeping all of these ideas in mind, is combining elements into an equivalent. And we're going to look at resistors first. You can do capacitors, but I'm looking at resistors first. And what happens is when there are many of the same circuit element in one circuit, and just that element, it is often convenient to combine them into a single equivalent element. Okay, so we can get more particular about what it means to be in series and in parallel, because this is where the definition of series and parallel really challenges students to identify whether resistors are in series or parallel and what order they're in. Okay, so series means that the circuit elements share the same current. Okay, that's what series mean. And parallel means that the branches share the same voltage. Okay, so when I think about things being in series and sharing the same current, that means that the current has no choice but to go through those elements one after the other. And when you're looking at the screen here, you may see that that would be the representation over here. The current leaves the battery, will flow in the clockwise manner in here. There's one branch, which means there's one current, and both of these resistors share the same current. That circuit can be simplified down to a single circuit represented by the battery, and I'm going to shorthand it, with some R equivalent. You can call this R equivalent, or you could call this R12 because it combines the resistors R1 and R2. R1 and R2 would get combined down to R12. So that's the equivalent resistor for this circuit. As opposed to the other circuit where we can see the branches share the same voltage. I see junctions here, so I can identify three separate branches. I'm going to have the top one, which I'm going to call I2. The middle one I'm going to call I1, and the bottom one I'm going to call I from the battery. And you can see that the currents are not going to be equal to one another. I battery is going to split up into I1 and I2, and so the currents are not the same current. This is not a series circuit. This is a parallel because the branches share the same voltage. From this point to this point, and you know, all along this wire, let's say this is a 9-volt battery, all along this wire, the voltage is 9 volts. Okay, so from this side of the battery, 9 volts, 9 volts, 9 volts. On this side of the battery is 0 volts on this side. So all along this wire, it's 0 volts, 0 volts, 0 volts. So it's 0 volts here and 0 volts here. And you can see these two branches share the same voltage. They share the battery voltage in this case. We'll see more complicated examples, but this is the simple example here. And when I simplify this circuit, this is what it would look like. I would have a long plate and a short plate for the battery, and I would put a resistor in here, and I would call it R equivalent, and I could call it just R12 because I took R1 and R2 and added them together for R equivalent. Okay, so you can see whether I have a parallel or a series circuit, I am simplifying both of those resistors down to a single element, some sort of equivalent resistance. So that's the idea of finding equivalence and how to look for series and parallel. I'm going to practice that more on a couple of problems, but let's focus on finding the equations for series and parallel. And what we do is we exploit what we know about what's the same and what's different between those circuits. So in a series circuit, you can see the series circuit here. The current is the same for the circuit elements in the series, right? And I drew that in here. Here's the positive plate and the negative plate for the battery, positive, negative for the resistor, and there is a single current flowing through that whole wire, and I'll just call that I. What we know is that the voltage in this loop has to be equal sum to 0, right? When I sum up the voltage over this loop, it will sum to 0. So if I do a loop here, I get V across the battery minus V1 minus V2 equals 0. And I can plug in what I know. Let's leave the voltage across the battery here just for a second. And I can plug in what I know about V1. That equals I1 R1, and V2 is I2 R2. And I'm going to simplify this even further. Even further, I'm going to say that I1 and I2 are equal to one another, right? I1 and I2, there's only one current here. There's no two separate currents. There's one current. It's the same current. So I1 and I2, I'm simplifying down just to that I. And I can see that I can factor that term out of here. So V across the battery, and I'm going to move this over to the other side, equals I R1 plus R2. And you can kind of see where this is going. If I simplify this circuit, let's do this. Here's the short plate and the long plate for the battery, and I have some R12 in my equivalent circuit. There's one current in here, I. And I've simplified R1 and R2 down to this one resistor. I have the same current here. So the voltage from the battery, if I plug this in, the voltage from the battery has to be equal to I R12, and that equals I R1 plus R2. And you can see how this proof works. So I get this equivalent resistance, which I'm calling RS. You could call it R12, R equivalent, whatever you want to call it in there. When we have them in series, you're just going to add all those resistors together. And if I have more than one resistor in here, I might have more than one. You would just keep adding them and summing them. And that's how that works. So that's where that equation comes from, is that the current is the same for all those resistors. It's the voltage that's different. So if I do a pretty simple example here, let's assign values to the resistors and battery in this circuit. What I'm going to do is, again, assign a current to this circuit. There's I, and I can do a loop. Here's the plus, minus, plus, minus, plus, minus. It simplifies down to this circuit. There's the long plate and the short plate of the battery. Here's R12. And I can write this out. R12 equals R1 plus R2. Well, I can see the values. R1 is 3, R2 is 6, and so I get R12 equals 9 ohms. So when I look at the equivalent circuit, this is going to be a 9 ohm resistor connected to a 9 volt battery. If I wanted to find the current in the circuit, notice that the current in this circuit is going to be this current same as the current in this circuit because there's only one branch. There's only one current ever. So how I would do that is say, like, the voltage across the battery minus IR12 equals 0. So I could find the current in this circuit. I equals the voltage over the battery over IR12. So that's 9 over 9. And so you get the current in this circuit to be 1 amp. And so that's how I would find the current from the battery, is to use an equivalent resistance for the rest of the circuit to find the current from that battery. Once you find the current from that battery, you can relate it to the other currents in the circuit, and in this circuit, it just happens to be the only current in the circuit. I could find V1 and V2. V1 equals IR1, which equals 1 times 3. So the voltage drop over R1 is 3 volts. V2 will equal IR2, so we get 1 times 6, so V2 equals 6 volts. So this is how this works, and when you're thinking about voltage drops across different circuit elements, what I'm going to do is follow the voltage in this circuit. I start out with 9 volts on this side, and I get to this side of the resistor, and it also has 9 volts. What I see is that there's a 3-volt drop over that resistor. So when I get to this side, it's going to be lower and it's going to be at 6 volts. All along this wire, it will be 6 volts. So there's 6 volts here as well. And you can see that this second resistor has a 6-volt drop over it. I go from 6 volts to 0 volts all along here, along to the back side. The short plate of the battery is going to be 0 volts. And so you can see at this point here, I have 6 volts. And they may ask you what's the voltage at a point or what's the voltage difference between 2 points. From here to here, it's 3 volts difference, a potential difference. But at this point in the circuit, there's 6 volts here. I wanted to choose a little bit more complicated series loop for us to work on. And you can see that here there's a couple of resistors, 4 resistors and 2 batteries. So what we're going to do is say that all of these resistors can be simplified down to 1 resistor, and the 2 batteries can be simplified down to 1 battery. And how do I do that? Well, Kirchhoff's voltage loop tells us that, okay? I have a 10-volt battery and a 30-volt battery, and it looks like they may add up, but I only have, when I follow this around, I only have 1 branch. I only have 1 current going through this circuit. And I'm going to put it in the direction that the dominant battery will cause it to go. Because when it gets here, the 10-volt battery wants to cause a current in this direction, but this is a 30-volt battery. So this current is going to dominate, and basically this 10-volt battery is causing a drop in voltage over it in the circuit. So it's not the wisest way to put a battery into a circuit, but that's what we have here. So there's 1 current through this whole circuit, and remember the strategy. We're going to assign a current, and then we can put plus and minuses over each one. So let's put plus and minuses over each circuit element. The current is going in the clockwise fashion, so I'm going to have potential loss over each one of these resistors in the clockwise direction. So this is the high side and the low side of that resistor. If I do a loop around here, notice that I will get this. Let's start at point A and do a loop around to point A again. So at point A, I get a 30-volt rise over that battery. I get a minus 27I, right? This is I don't know it, and the resistance on this is 27, and it's a drop. I come to the battery, that's the next circuit element in this loop. I get a loss of 10 volts here, minus 10. I can see because that's the second sign here is a negative. I have a drop over this battery. I also have a drop over this 12 ohm resistor, minus 12I, minus 8I, minus 5I. And then I'm back to point A again, and that's all of it. You can see when I simplify this algebraic expression, I get 20 minus 52I equals 0. And so I just solve for the I in the circuit. And the idea here is that we took all of these resistors. Notice that we took all of these resistors and we combined them essentially to 1 resistor. We took these 2 batteries and we combined them essentially to the same battery. So when I redraw this circuit, I just draw it like this. Here's the negative plate and the positive plate for a battery, the equivalent battery, and then I would have a equivalent resistor, and that's the end of it, our equivalent. And this is V equivalent. Notice with batteries, when they're in series, you would just add the batteries, whatever, if they're doing positives or negatives, take those into account. So that's the rule for adding batteries in series. So that's a bonus for this problem, is seeing that, how that happens. So that's what's going on this circuit. I'm finding the current in this circuit, I equals 20 over 52, which is 0.385 amps. Okay, and it flows in the clockwise fashion. we haven't answered the question yet. It says determine the voltage over the 8 ohm resistor. So I found the current in the series circuit. I found the current. If I want to find the voltage over the 8 ohm resistor, well, I would use Ohm's law again. It equals the current over the 8 ohm resistor, which we know is 20 over 52, or this number here. And then the value R of the 8 ohm resistor is 8. And when I multiply that out, what do I get? 8. I get 160 over 52. Well, when you simplify that down, it's 3.08 volts. So that's the voltage loss. Of the total 20 being delivered to the circuit, the 8 ohm resistor has a potential drop of 3.08 of those across it. So let's contrast two resistors in parallel. What we know about resistors in parallel is that the voltage is the same for each branch and the current splits. So I looked at this before. I had I battery coming up into here, and I have I2 and I1 splitting up. And that is the equation I'm going to start with. I battery equals I1 plus I2. Those are not the same values. But when I simplify this down to an equivalent circuit, I'm going to have the battery, so there's the plus and minus plate, and some sort of equivalent resistor, R12, so V battery. There's one current in here, I battery, right? This would be the current that came from the battery. If I simplify these two resistors down to the one resistor, this current I battery here is going to be the same current I battery here. So I can see that V battery equals I battery times R equivalent, R12. Or that I battery is V battery over R2. So I'm going to put that in here, V battery over R12. Well, I'm going to do the same thing for each of these. I1 is going to be V1 over R1. And I2 is going to be V2 over R2. Let's use what we know is the same for all of them. Voltage is the same for each parallel branch. And I only have these resistors, just these resistors in parallel. There's no other complex things going on. So what we know is V from the battery equals V1 equals V2. These are all the same value. And so you can see where the equivalent resistance equation for resistors in parallel come from. Okay, kind of nifty equation. If I had more branches in parallel, I would just add them on, etc. Okay, so that's what that means. This is a little bit more complicated of an equation to use. I see students stumbling on how to use this equation. Please remember that 1/4 plus 1/3 is not equal to 1/7. That is not true. I see students doing really creative simplification with this equation, but make sure you're very accurate with your algebra with this equation so you don't mess things up. What do I mean by that? Let's do a simple example. And again, I assigned 3 and 6 ohms for R1 and R2 and have a 9-volt battery. What I know is that there's 9 volts across each one of these resistors, right? From here to here, 9 to 0, 9 to 0, 9 to 0. Okay, and this is the plus side and the minus side. I assigned signs to all of them. So what I know here are equivalent. Let's find R12. Well, I would take 1 over 3, which is R1, plus 1 over 6, which is R2, and then I have to invert that, right? I'm inverting it. Originally, the equation was like this, but I want to invert it, and so what I'm going to do is whatever this is, I'm going to take the -1 value of it. That would be the same as having it look like this, 1 over that stuff. So that's how I do it. I put a -1 exponent up here, which means the reciprocal. So when I add 1/3 and 1/6, well, this is 2/6, right? I can simplify that to 2/6. I get 3/6 overall, and so I get the reciprocal of 3/6, which is 2 ohms. And what I'm going to note here is when you have resistors connected in parallel, notice this equivalent resistance is smaller than the original 2 resistors. When you do a series circuit, you get a larger resistance, but when you do a parallel circuit, you get a smaller resistance. And when I simplify this again, I can put the long plate and the short plate of the battery, and it simplifies down to this one resistor, and there's the battery. It may ask, like, what's the current delivered by the battery? Well, I battery has to be V battery over R equivalent based on Ohm's law. So I would do 9 volts over 2 ohms, and that equals 4.5 amps. So we're getting a larger current out of this same battery, still the same 9-volt battery, but we're getting a larger current and a smaller resistance because these elements are in parallel to one another rather than in series. So that's how parallel works. I wanted to talk about the equivalent resistance of more complex circuits. And you can see over here it might be intimidating, but if you systematically follow through the rules for combining in series and in parallel, you will be able to find an equivalent resistance for all of these resistors. Series and parallel can be found in a single circuit, so you can see that there is lots of that going on here. Tips and strategies for this. Follow the circuit methodologically through from one point to the other. So when I do this circuit, I'm going to start at A and follow it through methodologically to point B, and you'll see what that means. Redraw the circuit each time you simplify the resistors down. This is a step that I see students get lazy on. They try to hold all of the simplification they did in their head, and it gets messy on the paper. Just go ahead and redraw it, and then you have a clearer picture of the simplifications you made and can do more simplifications on it. Also, redraw it into something you recognize. This may not be the most intuitive way for you to think about a circuit and current flowing through the circuit. I personally like to put point A here. I assume that I might put a battery from A to B, and the current would flow in that direction, and so like I would put the 2 ohm up here. And notice that it's a different orientation. I redraw it into something that I can recognize and make more sense of, and that I encourage you to do that. You can redraw circuits as many times as you need to keep track of what you're doing. Finally, applying the definition of series and parallel. When I think about doing this in these circuits, I do think about in series having the circuit elements share the same current. So for example, in here, it may seem like this 1 ohm resistor and this 3 ohm resistor are in parallel with one another because they're geometrically drawn parallel in the circuit. But when I look at this branch over on this side here, I can see that the current leaves this junction, flows through this one, has no choice but to flow through these other two to get back and combine to the other currents. So these 3 resistors are in series. They share the same current. That's your test, okay? As opposed to branches that share the same voltage, the way I think about this is the current has a choice, and not that the current is, a human being making choices or anything. But when you draw it, you will see that there's a choice of that current to flow. For instance, once current flows through this 2 ohm resistor, it gets to this junction, and it has a choice of going through the 4 and 6. And when I redraw this on the page, I would draw the 4 here and the 6 over here, and notice that these are in parallel. They're not drawn that way to seem in parallel on this circuit representation up here, but when I redraw it, and that's the purpose of redrawing it, is to redraw it into something that makes more sense, and you can see series and parallel easier than with whatever you were given. So what I'm going to do is continue, and maybe I'll just grab this part of the slide right here and continue analyzing this circuit because that's my next problem. It says determine the equivalent resistance for the circuit, determine the current delivered by a 9-volt battery if we put a 9-volt battery in there, and determine the voltage over the 4-ohm resistor. So we have a couple of things to do here. So what I was doing was redrawing the circuit into something more recognizable, and I'm going to move that over here, and I'm going to move from left to right across this page, simplifying this circuit down. So here's my point A over here, and I said once I leave point A, go through the 2-ohm resistor. I have no choice but to go through the 2-ohm resistor. I get to this junction here, and I'll call this C, okay? I get to junction C, and there's a choice, okay? It goes to the 4-ohm or to the 6-ohm. Once it goes through the 4-ohm, it gets back to B, and I'm going to note that. After it goes through C, I have more things going on. Once it leaves C, I get a choice of going through the 3-ohm resistor. So I'll draw that 3-ohm resistor by itself. Or it can go through the 1 and the 2 and the 3 together. So let me draw that over on this side here. And so you can see that that single 3-ohm resistor and the 1, 2, 3-ohm resistor over on the far right are in parallel with one another. That whole branch, the 6 and all of this, is in parallel with the 4. And that whole thing is in series with the 2, and that will bring me back up to point A. And that may help you see better which resistors are in parallel and which are in series in order to simplify. And what we're going to do is look at the smallest portion of the circuit. The last thing I'm going to add together is this 2-ohm resistor. I have to do this stuff first. And before I do this stuff, I have to simplify this stuff. And before I simplify this stuff, I have to simplify these. So the first thing I'm going to do is simplify these. Okay, let me call this resistor little a. This is B, C, D, E, F, and G. Okay, so I just kind of went clockwise in here. So this is DEF. Notice this is DEF. I can simplify resistor DEF down to a single resistor. I'm going to note that these all are in series. This is series. And so I'm going to add them all together. Just R1 plus R2 plus R3. When I add those together, I get 6 ohms. Okay. If I were to redraw this, all right, when I redraw this portion, instead of having these 3 resistors here, I'm going to do this. I'm going to get rid of those 3 resistors. 3 resistors are gone, and I am going to have just a single resistor over here now, RDEF, and that's 6 ohms. This is a 6 ohm resistor. Now that I've simplified that down, maybe you can see where this is going. I can't do anything with this 6. These 2 are in parallel before they're in series with the 6. So I have to simplify these 2 down in parallel before I do anything else. So let's do parallel here. I'll just put parallel here. Let's do the equivalent resistance DEFG, right? The 3 ohm resistor is 3, is going to be 1/3 plus 1/6, right? We're doing the inverse relationship. And then I'm going to take the reciprocal of that, -1, and we're going to remember from the prior slide, that's 2 ohms. Not a big deal, okay? So instead of having these 2 resistors here in parallel, I'm going to get rid of them here, and I'm just going to have a single resistor, RDEFG, here. RDEFG, and this is a 2 ohm resistor. Now you're going to note that I can't do anything with this parallel branch over here until I combine these 2. These are in series. This is an 8 ohm resistor, and that's, let's see, 6. That would be resistor CDEFG. I've simplified all of these resistors here. All of these resistors here have simplified down to 8 ohms. Okay, so it's a little bit more manageable for me to draw. I encourage you to redraw every step, and I kind of did that. I just used the eraser. So I'm going to redraw over here. So this is the circuit I have now. all of this mess simplified down to there's a 4 here, an 8 here, and a 2 here. I need to, sorry, here's A and B. I haven't connected them yet. I need to simplify these two in parallel. So I'll go R, B, C, D, E, F, G. So all of this part of the circuit simplifies down to 1/4 plus 1/8. And I have to take the reciprocal of that. And that becomes, well, this is 2/8. So I get 3/8. Take the reciprocal of that, I get 8/3 ohms. 8/3 overall. The last step I need to make, here's point A. Here's a 2 ohm resistor, the original 2 ohm, A here. And then this 8/3 ohm resistor that represents the rest of that circuit. So the equivalent resistance for this whole circuit, R, A, B, C, D, E, F, G, when I add all of those together, I get 2 plus 8/3. 2 is what? 6/3. So I get 14/3 ohms for the whole circuit. And you can simplify that down. 14 divided by 3 is 4 2/3. So 4.6 repeating ohms. And that would be the equivalent resistance for this circuit. 4.6 repeating ohms. Okay, so you saw that I did it step by step by step. I went to the smallest parts, and you cannot make 2 branches parallel. I couldn't make these 2 branches parallel until I simplified these 2 resistors in series first. So watch out for your orders of operation here in regards to adding resistors. You have to add them piece by piece in order to get to the equivalent one, and you will have multiple steps as you move through the circuit. So let's answer the next question. I'm going to get rid of some of the information here I don't need anymore. Determine the current delivered by a 9-volt battery. So I don't need all of this. I'm just going to get rid of this and erase it like this is a whiteboard. And think about, well, now I have an equivalent circuit. Let's draw this equivalent circuit. I have A going over here. I have a 14/3 ohm resistor here, and then I go over to point B. And they tell me from A to B they want me to put a battery in here. So I'm going to put a long plate and a short plate, and that's the 9-volt battery that's been in here. When I do a loop, I can see that the voltage over that battery minus the voltage over that equivalent resistor is going to equal 0. The voltage over the battery will equal V equivalent, but I know that's I from the battery times R equivalent. Okay, if I put a battery in here from A to B, there's a current flowing out of it, and the 2 ohm resistor will get that battery, but once I get to this point that I labeled C, it's going to split up into more currents, and then it's going to split up into more currents here. And so all of these currents can be simplified down to one current in the equivalent circuit. So that's how that's working, is to have an equivalent circuit. For this, all of this mess, just get it down to one equivalent circuit. You can find the current there. We know the equivalent resistance, and we know the voltage across the battery. So the current across the battery equals the voltage over the battery divided by R equivalent, which is 9 volts divided by 14/3, which is 27 over 14 amps, which is almost 2 amps, almost, very close to 2 amps, 1.93 amps. Okay, so that's the current delivered by the battery. Once that 1.93 amps gets to point C, it divides up. But in this branch with the battery, it's 1.93. The last thing it wants us to solve for here is the voltage over the 4 ohm resistor. Okay, so it picked an easy resistor at least to get to. If I do a Kirchhoff's voltage loop just on the left side of my circuit here, I can see that I'll just do voltage rises and drops over here. Okay, I'll do and I'm putting my positives and negative signs in here so I can do a voltage loop around here, positive, minus. The currents are going to the left here and downward here, so that's how I get my plus and minus signs. The battery has a long plate and a short plate, and that's the plus and minus on the battery. So if I do this green loop here, I'm going to get plus 9 volts minus I from the battery times 2, right? The current, this 2 ohm resistor is getting I from the battery. And then this 4 ohm resistor is getting some other current, right? At point C, it splits up, so it's getting some less current, and I'm just going to call it minus I times 4. And those are the only 3 elements in here. I know I battery, and I'm solving for I, so I can solve for I in this equation. I am going to get 9 minus 1.93 times 2 divided by 4 when I do the algebra on that equation. So I get I over this 4 ohm resistor only, over the 4 ohm resistor only, 1.29 amps. So 1.92 amps goes this way. The rest of that, 1.93 minus 1.92, goes the other direction to the rest of this circuit. Okay, so that's how you would find the voltage over a single resistor, is relate the current that you already solved for to maybe a voltage loop or currents in junctions for the rest of the circuit. And that's how you would solve a complex circuit with multiple resistors.